So we described equilibrium potential, electrochemical gradient. How would you describe that? It's the net force acting on an ion. It's the combination of the electrical gradient and the concentration gradient. Those are both forces. Which membrane potential provides the strongest EC gradient for sodium? The choices at the bottom range from -100 to +100. Which one gives you the strongest gradient? The one that's closest to sodium's equilibrium potential, or the one that's furthest from it? Right? Because the closer you get to an ion's equilibrium potential, the weaker the EC gradient becomes. And to remind you of that, when you're actually at the equilibrium potential, the EC gradient is 0. So if you start moving away from that voltage, away from -94 for potassium, or away from +65 for sodium, then the EC gradient gets stronger, stronger, stronger. So from those choices, which one provides strongest EC gradient for sodium? -100 millivolts. Because you're 165 millivolts away from its equilibrium potential. How about for potassium? +100. Right? That's the furthest you can get from -94 given the choices. The further you get from the ion's equilibrium potential, the stronger its EC gradient becomes. The closer you get to its equilibrium potential, the weaker its EC gradient becomes. When you're at the ion's equilibrium potential, there is no EC gradient. It's 0. Let's take a look at the slides I put on D2L. It's a little extra info from 430.
Each one.
Let's look at it.
So it's under lecture slides, underneath the chapter 18 lecture slides. I'm going to download it so we can actually see the whole thing. So this is just a reminder of what's going on at rest, what's responsible for the resting membrane potential. And that is lots of leak channels for potassium, relatively few leak channels for sodium. So a lot more potassium constantly leaking out, very little sodium leaking in. As you constantly lose positive charges, because potassium is positive, what does that do to the inside? Keeps it negative. How negative would the membrane potential be if there was no sodium coming in, only potassium going out? It would be -94 millivolts. Potassium would just continue to leave until the membrane reaches its equilibrium potential, -94. And then potassium would stop moving. So why is it a little more positive than -94? Why is it -70? Because there's some positive charge coming in. There's some sodium coming in. So if you compare two different cells, a muscle cell at -85 millivolts and a neuron at -70 millivolts, Which one has more sodium influx at rest? Which one must have more sodium leak channels? The neuron, because it's further from minus 94. What's the role of the sodium-potassium pump? It's got one function. A lot of people think it's to repolarize a membrane. It does not do that. It has nothing to do with repolarization. It's to do one thing. It's to keep the concentrations of sodium and potassium stable. Keeps sodium high out, keeps potassium high in. That's the job of the sodium-potassium pump. When do they run?
All the time.
All the time. They never stop. So they couldn't be responsible for repol. It's not like they suddenly switch on at the end of dipole and they repolarize your membrane. What is responsible for repolarization of a membrane? Potassium efflux. Right? Either through leak channels, which is what happens in a graded potential, or through voltage-gated channels, which is what happens in an action potential. This is similar to what I did on the board. I changed the length of the arrow. Here they changed the thickness to represent the strength. If you start at minus 70 millivolts, and you have a given concentration of potassium, so the size of the arrow reflects the force of this concentration gradient. This represents your electrical gradient. Well, the concentration is bigger. They're in opposite directions. You take the difference, and that is your electrochemical gradient for potassium at minus 70. But if we change it from minus 70 to minus 94, what's going to change? Does the concentration gradient change?
No.
No, it has nothing to do with voltage. So what does change? The electrical gradient. Right? Did it just get stronger or weaker as you made the membrane more negative? You went from minus 70 to minus 94. So there's even a stronger pull on potassium to bring it in, because the inside is that much more negative, indicated by a bigger arrow. These are equal in strength, but opposite in direction. So what's the EC gradient for potassium when the membrane's minus 94?
0.
It is 0. There is none. Minus 70. Sodium has a concentration gradient directed in, has an electrical gradient directed in. You add the two together, there's your EC gradient. You change it to plus 65. What happens to the concentration gradient? Nothing. What happens to the electrical gradient? Changes direction, right? Because the inside was negative, now the outside's negative, and sodium's attracted to the negative exterior. So based on the electrical gradient, it wants to go out. At plus 65, they are equal in strength, but opposite in direction. No EC gradient. This is like a little virtual experiment. Just kind of run it in your head. We have a membrane. It's not allowing any ions to move, so it's impermeable at the moment. And it has no separation of charges. Membrane voltage is 0. All of a sudden, we're going to start opening channels for potassium. When you do that, what happens? Potassium starts to leave, right? You're starting at 0 millivolts. There's no electrical gradient. It's purely concentration. And it's very concentrated inside. So it starts to go out down its concentration gradient. But what's the consequence of potassium going out? It creates a membrane potential, right? Because you're losing positive charges from the inside, gaining negative, wrong way. You're losing positive from the inside, gaining positive on the outside. So the inside starts to become negative. The outside starts to become positive. And now you have a voltage of, let's say, minus 10 millivolts. Your concentration gradient doesn't change, but you are now developing an electrical gradient directed in. And as you go from minus 10 to minus 20 to minus 30 to minus 40, because potassium keeps leaving, what's happening to this electrical force? As your number gets bigger, the force gets bigger. minus 10, minus 20, minus 30, minus 40. How far do I have to go until the electrical force is equal in strength compared to the concentration? Minus 94. And as soon as you hit minus 94, equal but opposite in direction, potassium stops moving. You're at its equilibrium potential. Same thing for sodium. Suddenly open channels for sodium. No voltage at first. Starts coming in down its concentration gradient, but as it does, it starts making the inside more positive. Plus 10, plus 20, plus 30, plus 40. What's happening to the electrical force as sodium continues to enter? It gets stronger and stronger and stronger. And it's opposing that concentration gradient. How positive do you have to make the voltage to exactly counter the chemical force? You got to hit plus 65, and now you have a strong enough electrical gradient to offset the concentration. So now you're at the equilibrium potential for sodium. This one's from our textbook. The previous two are from other books, but you have this on D2L. So this is going back to the resting membrane potential, showing you the relative concentrations. The sodium-potassium pumps are responsible for that. At rest, all you have open are leak channels. But remember, you have a lot of leak channels for potassium, very few for sodium. So you have constant leakage of potassium, keeping the inside relatively negative at about minus 70 millivolts. The little bit of sodium coming in is what keeps the membrane a little more positive than minus 94, like minus 85 in a muscle cell or minus 70 in a neuron. But if there was literally no sodium leaking in, what would the resting membrane potential be? It would be potassium's equilibrium potential, because it would be the only ion moving. I think I have a little statement on the study guide that summarizes that. Yep, so it's at the top of the page. It says recall equilibrium potentials and electrochemical gradients from Neurophys, chapter 11. E ion, the equilibrium potential of an ion, refers to the membrane potential at which the electrical gradient pushing the ion in one direction is equal and opposite of the chemical or concentration gradient pushing the ion in the opposite direction. So here's the little summary statement I was referring to. Rule of thumb, as a membrane's permeability to a particular ion increases relative to that of the other ions, the membrane potential moves toward the equilibrium potential of that ion. So if we keep the potassium leak channels as they are, but start adding more and more and more sodium leak channels, what's going to happen to the membrane voltage? It's going to move away from minus 94, which is potassium's equilibrium potential, and it's going to start moving towards what? Plus 65. It's going to start getting more and more and more positive. And what if we took all the potassium leak channels away and only had sodium leak channels? What would that membrane's resting potential be? Plus 65. Just by looking at a membrane potential, you can assume which ion is responsible for it, if you know the equilibrium potentials of the different ions. So just the fact that a resting membrane potential is really close to minus 94, like minus 85, minus 70, that tells you potassium. Potassium movement is what's keeping it so negative. You know that the membrane is much more permeable to potassium than any other ion. But if we happen to see resting membrane potentials of, say, plus 50, then what would you assume? That there must be way more leak channels for sodium, and sodium movement is really responsible for maintaining that resting potential.
At plus 30, though, does it work? Isn't it at plus 30, though, where it like reverses or repolarizes?
That's an action potential. We're talking about resting membrane potentials. Yeah.
We're just at resting membrane potential. We're just focusing on
Say again, sorry.
or like the resting membrane potential, or are you just focusing on the channel?
Right, yeah. Because all the gated channels are closed. So what's responsible for the resting membrane potential? Leak channels. What's responsible for an action potential? And this is why you can't combine the two. Voltage-gated channels. All right, so that's my brief review of neurofits.
What is the membrane?